Hello all, welcome to the webinar series of IEEE Joint MTT, APEMC and CAST chapter. I'm Dr. Noshirwan. I'm the chair of this chapter and also working at Associate Professor at Research Institute for Microwave and Millimeter Wave Studies, also known as RIMS, at National University of Science and Technology, Islamabad, Pakistan. So we are located in Islamabad. Islamabad is the capital of Pakistan. It has both natural beauty and the business hub, and it is a place where we'll conduct our first of its kind IEEE International Conference on Microwave Antennas and Circuits, also known as ICMAC. And I hope that you guys will visit Islamabad and present your research. So National Institute of Science and Technology has several campuses, and this is a bird eye view of the Islamabad campus, a very well managed campus. And here you can see the building for the RIMS. This RIMS is a specialized institute, also known as Research Institute for Microwave and Millimeter Wave Studies. Apart from the faculty, foreign faculty and resources, we have some specialized state-of-the-art research facilities, including an anechoic chamber that goes up to 40 GHz. We have the electromagnetic compatibility interference lab that is used for teaching as well as for consultancy purposes and testing as well. We have microwave research and antenna lab and PCB fabrication lab under one roof. The idea to have all these facilities under one roof is to give an opportunity, a unique, I must say, opportunity to the students that in addition to their theoretical work, they will also gain knowledge by gaining the hands-on experience, and this will help them in their future career as well and getting some good jobs and PhD opportunities. So as you know, COVID-19 pandemic is a difficult time for all of us, and we have to take maximum advantage of this opportunity on the other side as well. So we have started a webinar series in March 2020 and conducted a number of webinars from well-known researchers and professors around the world. And today we are happy to announce that this is our webinar number 30, and our speaker is Dr. James Schellenberg from QuinStar Technology USA. A few words about the Dr. James. Dr. James Schellenberg received the BS degree in electrical engineering from Francisco State University, Francisco CA in 1969, and the MS degree in electrical engineering from Johns Hopkins University, MD in 1973. From 1969 to 1978, he was employed by Westinghouse Electric Corporation Advanced Technology Laboratory in MD, where he was responsible for bipolar and FET power amplifier and combiner design. From 1978 to 1988, he was employed by Huggies Aircraft Company Microwave Products Division in Torrance, CA. There he was responsible for many industry firsts in gallium arsenide hybrid monolithic IC technology, particularly at millimeter wave frequencies. From 1988 to 2005, he was with Schellenberg Associate developing power mimics for millimeter wave applications. From 2005 to 2008, he was with Trex Enterprises developing millimeter wave imaging radars. In 2008, he joined QuinStar Technology as a chief engineer. He is an inventor of the Radial Line Power Combiner and the Dolph Planar Power Combiner, has pioneered the development of hybrid monolithic FET amplifiers, oscillators at millimeter wave frequencies. He has been awarded the 1978 IR 100 award for the FET Radial Line Power Combiner and 1981 ISSCC winner award. He is the author of 8 US patents and more than 70 technical papers. His current research interests include nonlinear analysis and modeling of power amplifiers, high power broadband amplifiers and combiners, and millimeter waves GaN power amplifiers. Today he will deliver a talk, a very interesting talk on millimeter wave GaN power amplifier technology to power the future. And we are very happy and pleased to host him. He's also the distinguished micro-lecturer of IEEE MTT Society. So without any further delay, I request Dr. James to please proceed ahead and start the presentation. Over to you, Dr. James.
Okay. All right. Give me a couple seconds here to get everything set up correctly. Let's see, how do I make this full screen now? Okay, can everybody see this?
First, you have to share the screen, Professor.
I'm sorry?
You have to share the screen first and then make the full screen.
I thought I did that. But,
maybe you repeat again. Thank you.
huh. I don't see the up arrow again. It's disappeared. I don't know what's happening.
So maybe the simplest way is to, I think, close the PPT file and then open it again. I think this is a simple solution.
Okay. Whoops. Can you see my PowerPoint?
Sorry, I can't see because I can't see the share screen from your side. So first you have to share the screen.
Well, there was an up arrow, which I did check.
Yeah.
It's not here now.
Mm-hmm.
Not sure what to do.
So do you have the PPT in front of you?
Have the what?
The presentation file?
Yes, it's on screen.
Yeah, maybe you minimize that one.
Yes.
And then I think on the, if you have the MS Teams view in front of you, you can see the arrow button.
No, it's not there.
Oh, so let me see from here. Mm-hmm. Did you find something?
No, I've got the Teams window open, but there's no up arrow. I don't know what to type, what to do.
Maybe you have to maximize the window, because if you remember, we just before starting the talk, we have done this practice and you are seeing the arrow button. So I'm sure it will be somewhere around you.
Well, I maximized it and there's still no up arrow. I did click on it when you first introduced me.
Okay, right.
But it's disappeared now.
Yeah, actually, because at that time I was presenting, so that's why it don't allow you to share your screen, because I'm acting as a producer. But now at this moment I have closed my sharing screen, so I'm sure the easiest thing is that maybe you can close the MS Teams and join again. I will call you. I will include you in the session.
All right, I'll close the screen, so you'll call me.
Yeah, maybe you leave the session, I call you again.
Okay.
Okay, perfect. Perfect. So I can see you again now. So I hope you can see the share screen button now.
I can, and I'm going to click on that.
Sure.
And I'm going to do desktop like we did before.
Perfect.
And you can see my desktop now?
Yeah, I can see. Thank you.
All right. And I'm going to go full screen with this.
Perfect. So you are good to go. Thank you very much.
All right. Sorry about that, all of you out there. My name is Jim Schellenberg, as the chairman said, and I'm going to be talking about millimeter wave GaN power amplifiers, and specifically related to 5G. Okay, here's an outline of my talk. My introduction will basically introduce 5G and why millimeter waves are important to it. And we'll get into, as part of the introduction, the SSPA requirements for 5G, and why GaN is important as well. After that introduction, I will introduce the GaN device structure, give you a little more information on the physics of the device, and then go through a series of GaN benchmarks, basically intended to show you the state of the art, where it is today in terms of power, frequency, and bandwidth, efficiency as well. And then we'll get into a series of slides talking about the requirements and some of the results that are out there today for MMIC specifically intended for 5G. Finally, I will talk about GaN limitations, future trends, and then give you my conclusions. All right, so what is 5G? Well, in a nutshell, 5G is simply 4G with increased speed, increased capacity, and reduced latency or delay. We are talking about with 5G a times 10 increase in data rate up to a peak data rate of 20 gigabits per second, a reduced latency from typically 50 milliseconds down to around 1 millisecond, and a times 100-fold increase in the number of connected devices per unit area. As of first part of this year, 2021, all three major US carriers have some form of 5G service available. However, the service is only available in the large cities, and even within the cities, it's rather sporadic. My opinion, it will take several years yet for it to be widespread in the cities, and then progressing to the suburbs and possibly, at least to some degree, into the countryside. All right, potential applications for 5G. Obviously, due to the higher speeds 5G will have, we'll be able to download things. Specifically, the example I give here is a movie. We don't download movies very much like we used to, but in any case, if you were to download a movie with 5G, you could do it in about 10 seconds. And that is opposed to with 4G, it takes anywhere from 10 minutes to 15 minutes. Car-to-car and car-to-infrastructure communications, 5G is expected to be a great aid to that. Basically enable the autonomous vehicle. So it's expected to be a great boon, a benefit to car-to-car communications. The IoT, the Internet of Things, basically home communications, the density, the number of connections per unit area will be a benefit there. In the e-health area, we all have smartwatches, or at least some of us have smartwatches. And 5G will really enable a lot more things. For an example might be, you're on the golf course, you're doing your golfing, and suddenly you have a heart attack. Well, with 5G and a smartwatch, the watch will detect the fact that you're having a heart attack, will automatically contact your doctor, summons an ambulance, and let the hospital know you're on your way. Smart cities, 5G is expected to really enable traffic management in conjunction with sensors at every intersection. It should allow people to move seamlessly through the major city tie-ups and traffic jams. In M2M, machine-to-machine communications, the latency is going to be important. Reducing that to 1 millisecond is expected to be a big benefit. And then there are always unforeseen new applications that pop up, totally unseen and unanticipated. We've seen that in the past with 4G and 3G. And these new applications often become the dominant reason for people wanting to upgrade. Speed requires bandwidth. You know, there's there's a fundamental property of nature that if you want to send more information more rapidly, you need more bandwidth. There's just no way around it. 5G accomplishes that. One of the ways it does this is it opens the channel bandwidth up from, normally it's 20 megahertz with 4G, up to 100 megahertz. So that's a 5-fold increase. And a given cell site might have 8 or more channels available. So it's easy to see that with 100 megahertz wide channels, if you have 8 or more, you can quickly require a bandwidth of a gigahertz or more. It's not uncommon to have more than a bandwidth requirement for a given cell site. And there's simply not a lot of bandwidth around available for this. The spectrum is fully occupied below 6 gigahertz. There's a spectrum allocation chart in the middle of your graph there. It gives you an idea of how congested the spectrum is, certainly within the United States. It's fully occupied all the way to, well, basically 30 gigahertz. There's certainly no gigahertz wide available chunks of bandwidth until you reach millimeter waves, which is 30 gigahertz. Again, for those of you that may not be familiar with the spectrum designation, the millimeter wave spectrum is from 30 to 300 gigahertz. Or if you think in terms of wavelength, from 10 millimeter wave wavelengths to 1 millimeter wave wavelengths. Okay? All right, so the ruling body in the US for spectrum allocations is the FCC, and they have designated 3 major bands, what they call a low band, a mid band, and a high band. The low and mid bands, there's relatively small amount of bandwidth available. The high band contains almost 5 gigahertz of new bandwidth dedicated solely to 5G. And the sub-frequencies, well, these are the frequencies, bands 28, 24, 37, 39, and 47 gigahertz are the major sub-bands within the high band. And these are the millimeter wave frequencies. These are the frequencies where you're going to have the high speed. And the use of the other bands, well, they're part of 5G, are not going to provide the speeds that we're talking about. There's also some unlicensed bands, really, that go up to as high as 95 gigahertz that are primarily for Wi-Fi and other uses. We won't get into those. All right, so here's a little more detail on the high band. This is the millimeter wave frequencies. These are the frequencies that we're going to be talking about here, and these are the high-speed frequencies, the high-speed bands. So we have, again, sub-bands of 28, 24, 37, 39, and 47 gigahertz. Altogether there, we have about 50 channels available of new bandwidth and 5 gigahertz of bandwidth. So this is where the high-speed channels are going to reside in the high band. All right, so let's talk a little bit about 5G architecture. We've already identified the frequencies that are going to be used for 5G. But the architecture, the major difference, of course, is the use of millimeter waves. This is the first time that cell phone service or the new generation, 5G generation, has ever used millimeter wave frequencies. This is the first. Now, millimeter waves, as many of you know that work in the industry, is basically line of sight. It doesn't readily penetrate buildings or trees, other obstructions. You need to go around them. So what 5G does, the basic philosophy behind 5G is to create a lot of small cell sites. And these small cell sites are located strategically within the cities to route the signal around the obstructions to the customers, to the cell phones. This is shown in your little cartoon on the lower right. The cell sites are quite small, can be as small as 200 meters in diameter. And so there's a lot of them, and there's a large number of small, low power, because they're small, cell sites. Now, this is anticipated to cost on the order of $2.7 trillion, that's trillion with a T, worldwide in order to implement. So it's going to be a massive, certainly a massive undertaking worldwide. This slide basically addresses the subject of where do we need millimeter wave SSPAs in the system. And the system is kind of busy, apologize for that, but basically you have your data center on your far left, and you have your cell sites, base stations located around the area. And you can see the signal is routed from the data center to the base stations and then to the cell phones. In order to get non-line of sight service, in some cases you have to go around or use obstructions, actually bounce the millimeter wave signal off some of the obstructions to reach your customers. Okay, there are three basic locations we need power amplifiers for this system. There's the transmitter for the handset that will require, because the cell sites are relatively small, only a couple hundred milliwatts of power. And now the base stations themselves, the transmitters, will require solid-state power amplifiers. Those amplifiers were around 2 to 20 watts, and also for backhaul. So you have three applications for SSPAs. You have the handsets, the base stations, and the backhaul. So those are the three. And you can see the power levels basically that are required. Okay, so this is a summary of the SSPA requirements. We've seen already that there are three bands, but it's primarily the high band, that the millimeter wave frequencies that we're interested in here. Those are the ones where we're going to have the high-speed communications. For power amplifiers, the power levels, we're going to need 2 to 20 watts for the base station and backhaul, and only a couple hundred milliwatts for the handsets. 100 megahertz channel widths, modulation. Efficiency is particularly important for the handsets. That's fairly obvious. To maximize battery life, you need an efficient amplifier. Although I should point out that since the power level is much lower, the demand for power on the cell phone is much less. So yeah, it's important, but probably not as important as it was for some of the other higher power handsets, cell phones in prior generations. Okay, for base stations, backhaul, you need linear power. Peak power, or I'm sorry, saturated power is not what you need. You need high efficiency and you need reliability. All right, so with all that information in hand, let's examine semiconductor technologies that are out there today and see which technologies might be suitable. This is a graph of semiconductor technologies versus frequency and power. And as you can see, the bottom of the chart, silicon, germanium, and CMOS, the silicon technologies are the lowest in cost and really dominate the low power, lower frequency spectrum, certainly up to 20-30 gigahertz. They're dominant. At power levels above a couple watts perhaps, and at higher frequencies, gallium arsenide appears to be the technology of choice. And if you're going to higher powers and higher frequencies yet, GaN on silicon carbide is the dominant technology. GaN is good all the way through 100 gigahertz, And at lower frequencies, several hundred watts are possible using GaN on silicon carbide. So here is a chart that shows the 4 common semiconductor materials and kind of explains why silicon carbide and GaN dominate. Your second column there, you see the band gap energies. Silicon and gallium arsenide are both relatively low, 1.1 to 1.4, and silicon carbide and GaN are much higher, up in the 3s, 3.2 to 3.4. Notice that the critical breakdown field, column 3, there's a corresponding increase in that quantities there. There's an order of magnitude difference in critical breakdown field from the silicon and gallium arsenide materials to silicon carbide and GaN. And this, incidentally, is why silicon carbide and GaN dominate higher frequencies, is because of the critical breakdown field, and this allows the device to operate at much higher voltage. And this, in turn, provides much higher power. I want to also point out that silicon carbide has excellent thermal conductivity. And as you will see in a moment, that's why it's often used as a substrate material to extract the heat. All right, so before getting into millimeter wave GaN, I want to talk a little bit about XKU band GaN devices, mainly because they were here first and they give us a lot of you might be familiar with those type of devices. The device structure is shown on your right. Excuse me a second. You can see the cross-sectional view of the GaN HEMT device. Again, I want to point out these are HEMT device, high electron mobility transistor type structures. And they're fabricated on silicon carbide or in some cases silicon substrates. And we grow our GaN channel directly on the substrate. And on top of that, we grow an aluminum GaN layer. This becomes a donor layer for the electrons which form the 2D gas. On top of the aluminum GaN, we have our source and ohmic contacts. And then in between the source and drain, we have the gate, Schottky gate. Note that there's a rather unusual electrode there shown called the field plate. The purpose of the field plate is to moderate the intensity of the E field on the drain side of the gate. And this in turn allows us to operate this device at much higher voltages than we could without it. With this structure and a 1/4 micron gate length, that's the length of the gate in the dimension between the source and the drain. These devices operate with Fmax of typically 100 gigahertz, Ft of 40 gigahertz, and a rather outstanding breakdown voltage of 120 volts. This allows for a drain voltage of 28 to 40 volts for normal operation. I should point out, I've worked most of my career with gallium arsenide and indium phosphide, low voltage type materials. And with those materials, typically you might have a 15, 20 volt breakdown if you're lucky. So to work with devices that have a breakdown voltage of 120 volts, I find rather astounding, and of course a great pleasure to work with. Is they're very rugged, they're very tough devices, almost indestructible. As I said, these operate normally 28 to 40 volt drain operation. High power density of 10 watts per millimeter of gate periphery. Now, what I mean by that is that these GaN devices are scalable. In other words, the more gate periphery a device has, the higher power in general it can achieve. And this is a figure of merit that we often, and you will see I will use that throughout the remainder of my discussion. The power density is how many watts of power can we get out of a unit of gate periphery? Example being, if I have 1 millimeter of gate periphery device, I should be able to extract 10 watts out of it. Now, that's ideal. That's if the matching circuit and everything is operating correctly, you have the correct bias and everything, then you'll get 10 watts out of 1 millimeter. And if you had 2 millimeters of gate periphery, you'd get 20 watts. Of course, it's scalable. So that's an important figure of merit as we move along here. So with that in hand, let's take a look at a millimeter wave GaN device. And that structure is shown on your right. It's quite similar to the XKU band device, which I should point out is good to perhaps 20 gigahertz operation. This structure I'm showing here is good through, with some minor modifications, up to 100 gigahertz. As you can see, it's very similar. Substrate is perhaps thinned a little thinner. We typically use 50 microns for the highest frequency of operation. You have the GaN channel and the aluminum GaN layer, source drain ohmics. Spacing is tighter. Everything is tighter here. Source drain spacing typically 1 micron, as opposed to 2 to 5 microns for a XKU band device. The gate length, of course, is also smaller, and that's typically 1/10 of a micron. But notice the major difference here is the absence of the field plate. We no longer have a field plate on the edge of the gate, between the gate and the drain. And the reason is we can't afford the parasitics of that field plate. It degrades the frequency response. It degrades it to the point where we just can't tolerate it. And so devices that are designed to operate at millimeter wave frequencies don't have a field plate. The net effect of the absence of the field plate, of course, is a lower breakdown voltage. And as opposed to 120 volts with XKU band devices, millimeter wave device breakdown voltages might only be 50 volts, 40 volts, and at the highest frequencies, probably as low as 30 volts, or perhaps even a little lower. Everything is more compact. As I said, the source drain spacing is 1 micron. As a result of that, there's a lot of high power density and some degradation of response. And notice the power density, the last quantity here, the last item on the list, is now 3 to 4 watts per millimeter. And that's really due to the voltage being lower and the power density being higher. So we've reduced from 10 watts per millimeter for XKU band devices down to around 3 to 4 watts for the millimeter wave GaN devices. Okay. All right, so this slide is basically a summary of everything you've heard. There's a couple items here that you haven't heard yet, but number one, why does GaN dominate? Well, the primary reason is the high operating voltage. At K-band, we typically operate around 24 to 28 volts, and this provides us a factor of 5 to 10 higher power levels than we can achieve out of other technologies, gallium arsenide or indium phosphide. The higher voltage also allows for higher impedance levels, which results in reduced matching circuit losses. The substrate, silicon carbide, is an excellent substrate material. It's a low loss dielectric, and we can fabricate our other passive elements on the same substrate with the active device. Our inductors, capacitors, resistors, transmission lines can all be fabricated directly on the silicon carbide to form our MMIC. Due to the high band gap, we can operate at much higher temperatures than we can with gallium arsenide. Channel temperature max is typically 225 degrees C as opposed to 150 with gallium arsenide. GaN devices are not breakdown limited. They're thermally limited. But because of this, you can operate a GaN device in a pulse mode and achieve higher pulse power operation. which is useful for some applications. Okay, as a result of the above things, we've seen a tenfold increase in millimeter wave power, primarily due to GaN in the last 10 years. So GaN has provided a major boost in power levels. All right, so if you're going to design your own MMIC for some application, millimeter wave MMIC, you're going to need a foundry. Most of us don't have a foundry in our organization, so we have to go outside to an outside group or foundry to have somebody else fabricate our designs for us. And I've listed here 6 foundries worldwide. The first foundry I have on my list is HRL Laboratories in Malibu, California. They're the first. They're the people that really started the millimeter wave GaN. And they've been offering a foundry service for 10 years now and are the premier foundry for the highest frequency of operation. They're not very cheap. They're quite expensive, but if you need to fabricate MMICs operating, say, above 60 gigahertz, they're really the only place to go. The next 3 foundries, Northrop Grumman, Qorvo, and BAE Systems, all have, of course, different processes, slightly different, gate lengths, etc. But the net result is very similar. I've used all the foundries on this list here except for OMIC. So I have personal experience working with all these foundries. And these 3, Northrop Grumman, Qorvo, and BAE Systems, all have about the same performance, with Northrop Grumman probably having a slight advantage in efficiency. They're all, the cost is moderate for these 3 foundries. The key parameter, power density, they're all running about 4 watts per millimeter. And the processes are good for device operations up through 50 gigahertz, perhaps a little higher, maybe 52 to 55 gigahertz at the most for all 3 there in the middle. The final 2 foundries I've listed here in my table, I've included because they're lower cost. The performance is not quite as good as the middle 3, but they do offer a lower cost process. Okay, so let's move on to a series of GaN benchmarks. These benchmarks are designed to basically show you, tell you where GaN technology stands today in terms of output power, efficiency, and bandwidth at millimeter waves. All right, so the first chip I'm going to show you holds the record for the highest output power for a single chip. And this was achieved over 5 years ago now, back in 2015, and it still is the record for the single highest power for a single chip of gallium nitride, almost said gallium arsenide. 40 watts at 27 gigahertz with an outstanding 37% PAE. Now, you might say, well, 27 gigahertz, that's below 30, so that's really not part of millimeter waves. Well, yes, that's technically correct, but I'm including it because there are some important frequency bands for 5G that are below 30 gigahertz. And so for the purpose of this discussion, 27 gigahertz will be part of millimeter waves, at least for today. Okay, so that's an excellent kind of laboratory result. This chip, to my knowledge, is not available commercially, but that could change. I don't know for sure. The next chip, gee, I have to apologize for the photo of the chip here on the left. This was purposely blurred by the manufacturer. I suppose they want to hide their design secrets. But in any case, it's an excellent MMIC design. It holds the record for the highest combination of power and bandwidth. It covers 6 gigahertz from 32 to 38 gigahertz with a minimum of 10 watts output power and a peak power of 13 watts at 35 gigahertz. I should commend the chip manufacturer for the data sheets. The data sheet for this MMIC has extensive data available for both pulsed and CW operation under different bias conditions. So quite an impressive set of data in the data sheet. The chip size is very compact, only 9 millimeters squared. So it's one of the smallest chips that's out there, and this is commercially available. The next chip holds the record for the highest combination of power and PAE. This chip was reported on about a year and a half ago at IMS and achieved 8 watts with 42% PAE at 31.5 gigahertz. And this is just above the lower limit of our millimeter wave frequency spectrum. Okay, that is an R&D result. It's not commercially available. The next chip I'm showing you here holds the record for the highest power density, that is in terms of watts per millimeter. And this is at 35 gigahertz, so it's certainly not at the band edge anymore. 35, it produced 16 watts of power, which corresponds to a power density of 4.4 watts per millimeter at a rather high 34 volts. Chip size is relatively large. You can see that's twice the size of the Corvo chip. So, but it is commercially available, so that's certainly of note, of importance. The next chip I'm showing you here holds the record for the broadest bandwidth at millimeter wave frequencies and the highest power over those bandwidths. This result was reported, it's been 5 years now, and it's still the record in terms of output power and bandwidth at millimeter wave frequencies. It produces a minimum of 2 watts across the 75 to 100 gigahertz band, and a peak output power of 3 watts at 84 gigahertz. And it uses a rather novel traveling wave structure to achieve this broad bandwidth and power. Okay, and that is an R&D result that's not available commercially. And finally, I have a chip that I want to show you. This is a rather interesting CPW design. The other chips, as you've seen, are all microstrip geometries. This is CPW, and this is a result by Fraunhofer in Germany. This represents the highest frequency of operation for GaN. This is not the highest frequency of operation for solid-state devices. However, indium phosphide and HBT devices operate well into the terahertz region. But in any case, this is the highest frequency of operation for GaN, and it produced an output power of 0.44 watts at 120 gigahertz. PAE is not so hot, 16%. All right, so I wanted to put all these results into a single slide, plus I added a few more to fill in some holes. Basically give you an idea of where the technology stands over this broad frequency range. You can see, well, sorry, I'll back up. The triangles are power, and the blue squares are efficiency. And these are plotted from the lower edge of K band, 26.5 gigahertz, up through 120 gigahertz. Now, the red triangles, as you can see, the output power is typically around 20 watts at the low end of the band, perhaps 40 watts for the laboratory results. And as you go higher in frequency, that power level decreases as basically 1 over f squared. So by the time you reach 100 gigahertz, you're down to around a watt per millimeter. The Fraunhofer result is even a little bit below that curve at 0.4 of a watt. The efficiency, on the other hand, typically in the mid to high 30s at the low end of the band, with an R&D result of over 42%. And then as you progressively move to higher frequencies, that decreases, as you can see, into the 20s and then into the teens at the highest frequencies. The table on the right shows the individual results, which are plotted on the left. All right, so what do you do if you need power levels above these single chip power levels? Well, what you can do is use power combining techniques. There are basically two types, depending on the geometry of the combiner. There's the so-called planar combiners. An example might be the N-way combiner for that, corporate N-ways. And there's spatial or 3D combiners, which in that category we have the radial, grid, tray, and coaxial amplifier configurations. Advantages of a combiner system? Well, the obvious advantage is you achieve higher power than you could with a single chip. By combining multiple chips, we can achieve 10 times or even more, sometimes 20 or even higher times the power of individual single chip power levels. Another advantage might be with multiple chips, you can derate the power of individual chips, run them at lower current, let's say voltage, and they'll run cooler and live longer. This is particularly important for high reliability applications, say space applications, where lifetime is critical. Third advantage of a combiner system is that, at least in principle, if it's designed correctly, you could have one or more chips fail, and the operation of the combiner system would continue to provide useful output power. So it has the so-called graceful degradation characteristic. A disadvantage of a power combining system is that it's usually complex, costly, and a relatively large size. This is an example of a power combining system. This is a 4-way. Here I've combined 4 of the chips that I showed you previously, the 31.5 gigahertz high efficiency chips. And we're using a waveguide planar combiner, divider combiner pair. The divider on the left side, and we recombine on the right side. And that's a waveguide structure, a binary, 2-tier binary structure. And the performance of this amplifier is shown on your right. It puts out a total of 30 watts. The individual chips, you might recall, put out about 8 watts. So we're getting peak output power of about 45 dBm, or 30 watts with a very nice linear response. P1 dB and PSAT are very close to each other, which is a good characteristic for a linear power amplifier. Efficiency is just over 30%. It's reported on at IMS about a year and a half ago. Here's yet another example of a power combiner. This happens to be a radial combiner. And that's shown, the overall combiner is shown in your lower right. It's about 2.4 inches in diameter, very compact. It contains altogether about 24 mimics. 24 mimics combined in 2 stages. First, we combine 2 mimics and form a module, a two mimic module, and then combine 12 of these modules around this radial structure to form the combiner power amplifier. And as you can see, the performance on your left, it's producing over 40 watts output power across the 75 to 100 gigahertz band. Here's yet another example of a radial combiner. Here we're combining 16 1-watt GaN Mimics to achieve 12 watts at 94 gigahertz, quite a bit higher. This is also a very small, compact structure. You can see it's only inch high and 2 inches in diameter. All right, so I've shown you some of the state-of-the-art results for GaN. but I want to talk now more specifically about the requirements for 5G and how we can tailor these results for 5G requirements. Okay, 5G needs linear amplifiers. Most all the results I've shown you today were the performance of the Mimic at PSAT or near PSAT. And that just is not going to work for 5G. We need a linear amplifier, and not only do we need a linear amplifier, we would like this amplifier to be high efficiency as we back the power off it to maintain its efficiency. Typically, semiconductor amplifiers, devices, and I suppose tubes for that matter, achieve their best performance, highest efficiency at or near saturation. And as you back the power down, typical problem is the efficiency gets rather poor. And this, of course, is also happens with GaN devices, and it can be rather dramatic. We would like for 5G, for these amplifiers, to not only be linear, but as we back off the power to lower levels, that it maintain its efficiency as much as possible. The problem is shown on your right, where you have a typical TGA 2222 data. This is a Corvo Mimic operating at 35 gigahertz pulse. And it's a 10 watt Mimic, and that's 40 dBm plotted on the left side. You can see in order to achieve that power level, however, you have to drive the device well into compression, actually 6 dB into gain compression. And at that level of gain compression, it's pretty much useless for any kind of a communication application like 5G. To be useful, you would have to back down the peak power down to around basically 36 dB, let's say, instead of 40 dBm peak power down to around 34. At that power level, the linearity is probably acceptable, but the efficiency would be horrible, probably in the neighborhood of 3 to 4% on average with typical 5G modulations. So that's efficiency and of course output power. Linearity of this Mimic is really not acceptable for 5G. What we need is to improve both the linearity and efficiency. In order to do that, there's a number of techniques that have been developed over prior generations. These linearity and efficiency techniques are listed here. I don't have time to go through these and explain them basically, but I have an excellent reference I want to refer you to at the very bottom of the slide that basically can give you an overall view of these techniques and what they can do to improve both the linearity and also the efficiency of amplifiers running under back-off conditions. There are two techniques, however, that are important, and I want to point out at least. And the first is DPD, baseband. Most handsets today, 4G handsets, use some form of DPD at baseband. And basically what that means, that's digital predistortion in the handset to linearize the amplifier. Also, there's a technique called the DOHERTY, and we'll go into that a little bit here, but it's a powerful technique and it's an efficiency enhancement technique. It's a technique whereby we can maintain the efficiency as we back off the output power, at least maintain it to a degree. And I'll talk about that next. Here's a slide that shows the first ever DOHERTY GAN Mimic at millimeter wave frequencies. Again, the DOHERTY configuration was developed, I guess, back in the 30s for tube operation, but it has been adapted for solid state devices at lower frequencies. 4G and 3G before it have used it quite extensively. And again, it's an efficiency enhancement technique. It's to improve the efficiency under back-off conditions. And I'll just briefly describe it. Basic concept is that the amplifier has two parts. There's the upper half of the chip and the lower half. The upper half of the chip runs continuously and provides the power independent of the signal level, whereas the lower half of the chip is biased such that it's cut off, it's not operating, it's not using DC power at the lower power levels. And only for the peak power levels it turns on to provide the peak power levels that the chip needs to amplify. So in that means it has a second half which kicks in for high power levels to improve the efficiency at lower powers. And you can see this on your right here, at least to some degree. You can see the efficiency instead of diving at lower output power. It maintains itself somewhat. It's degrading, of course. Ideally, we'd like to keep the efficiency up at 30%, all the way down as far as possible. And then, of course, at some point it has to start to degrade. But this chip is doing a fairly decent job of improving the efficiency at lower back-off powers. You can see it maintaining its efficiency above 20%, all the way down to around 32, 33 dBm output power. So it's not perfect, but it's the one of the first attempts to apply the DOHERTY method of efficiency enhancement to millimeter waves. That was reported on about a year and a half ago at IEEE by CMOS BCICTS conference, November 2019. All right, all is not rosy in Gansville. Well, I've been telling you the wonderful and great things GaN has done and will do in the future, but there's some problems. First and foremost is cost. GaN is expensive, and that cost basically has ruled out the use of GaN, certainly for high volume commercial applications until now. I'm anticipating and hoping that 5G will be the impetus, will be the drive behind to create enough volume to allow GaN to become more cost effective. And I'm getting perhaps ahead of myself a little bit here, but there are two aspects of the cost here. Well, there's probably three. First of all, the small wafer. We're typically using a 3 to 4 inch wafer for GaN and running basically in a laboratory type mode with PhD engineers following the process. So it's certainly not cost effective, certainly for a production process. We need to progress to 6 inch wafers, and there's a start. There are some of the foundries today. There's a couple of foundries that are starting to offer a 6 inch wafer for GaN. Inherently, however, GaN is more difficult and costly, largely because of the silicon carbide substrate. It's one of the hardest materials known to man. It's difficult to lap and form via holes. It also has a relatively high defect density, 10 to the 7th, 10 to the 8th per centimeter squared, which is relatively high, and that contributes to the yield, and of course the yield goes down, the cost goes up. The last point there again, which is the volume, there just hasn't been enough volume to justify the investment in capital and procedures to get the cost lower, and I'm a firm believer that 5G will be the application which will drive costs down with GaN. There's a second problem with GaN, however, and that's called current collapse. Basically, what that is shown on your right. If you have a device and you operate, say, with a DC curve tracer, you might have the IV characteristics shown in blue. But then if you were to pulse that same device and use a progressively shorter and shorter pulse, the IV characteristics tend to collapse down to basically nothing. And it ceases to be an active device. The short pulses, of course, simulate high frequency operation. So what that means basically that at higher frequencies, the device simply does not operate as an active device. This is due to traps, long time constant traps in the interface layers, between layers, for instance, between the LGAN layer and the passivation layer. There are charges with relatively large time constants which are trapped at the interface level, and this causes this effect. This obviously will affect the power efficiency and gain of the device. However, the bright side of this is the fact that it doesn't seem to affect the lower frequency GaN devices very much. It's primarily a problem at higher millimeter wave frequencies. And what do I mean by higher? I mean above 50 gigahertz. At higher frequencies, 60, and at W band, 90 gigahertz, I see this quite frequently, and it's quite a problem. It can be a major problem affecting yield. However, at K band, there is always some degree of this IV collapse that will occur, but it's relatively minor at the lower frequencies. By minor, I mean less than 10%. On the optimistic side, this problem was seen with gallium arsenide back in the 80s and 90s when I was a young engineer. And of course, that problem has been solved. Gallium arsenide doesn't have this problem anymore. And in the same vein, I believe this problem will be solved. This is a materials growth issue, device fabricational issue, and I firmly believe that it will be solved as well, even at the higher frequencies with GaN. Okay, so our future challenges, we obviously need to solve the current collapse problem. From the previous slide, we need to reduce processing costs and defect densities and make the transition from 3 to 4 inch wafers to the 6-inch wafers. I'm showing you a 6-inch wafer on your right. And again, some foundries have started to make that transition, but it will happen as the volume requirements increase. Now, looking forward, there are some other materials and combination substrates, example being GaN on a synthetic diamond substrate that holds promise due to the excellent thermal conductivity of diamond materials. It's 5 times better than silicon carbide. Although I don't think that's going to be a relevant technology for low cost. There are also other new devices on the horizon, and I really don't intend to go into those except just to mention that they do exist and that people are continuing to work in the R&D phase, developing new combinations of substrates and semiconductor devices. I have a final challenge I want to leave you with here, and that is, will silicon ultimately dominate? I have a little story I want to tell you. When I was a young engineer starting out, I worked with a 3.5 semiconductor material, gallium arsenide at the time, and we were working at about, X-band frequencies, 10 gigahertz, low noise gallium arsenide devices, discrete devices at the time. And we were aware of the progress silicon was making. Certainly at that time, silicon was progressing into the VHF and UHF frequency ranges in both low noise and power. And we're kind of looking over at our shoulder, looking at silicon, wondering if this will eventually overtake us and overtake gallium arsenide in terms of prominence. But we console ourselves with the fact that silicon, yeah, they may make progress, but they will probably only reach a gigahertz, and if that, probably not much more. Well, you all have seen what silicon technology has done over the years. Not only has it reached 1 gigahertz, it has reached 10 gigahertz, and there are, of course, R&D results at over 100 gigahertz with silicon. And this is even in spite of the technical difficulties or inferiorities that silicon has over the other 3.5 silicon devices. Silicon continues to find ways of dominating at higher frequencies. So the moral of the story is never write silicon technology off. It continues to advance. Here are my conclusions for 5G. I think silicon technology will dominate the handset market since we don't need much power. We only need a couple hundred milliwatts output power. And this is a power level that silicon can readily and easily achieve. I believe it will dominate the handset market through 50 gigahertz. GaN on silicon carbide, however, I think will dominate the base station and the backhaul market at frequencies above 28 gigahertz and for power levels above 2 watts. You've seen a lot of the work that's been done in the 28 to 36 gigahertz region. However, a lot of work needs to be done to linearize these mimics that you've seen and to improve their efficiency under back-off conditions. Further, mimics need to be developed for some of the other 5G frequencies, namely 37, 39, and 47 gigahertz. Okay, thank you for that. That concludes my talk. I appreciate your attention. I'll turn it over to the chairman.
Thank you very much, Dr. James, for a very interesting talk. So we have few questions regarding the talk. So the first question is, normally the Foundry defines the absolute maximum rating for a GaN device. So how we can ensure or determine the power handling capacity of a microstrip transmission line used at the output of a GaN device?
You're referring to the limitation of the microstrip itself?
Yeah, that's true.
Okay. Yeah, there are limitations to how much power, depending on the dimensions of the microstrip structure. You know, we did a study of that back some time ago. Off the top of my head, I can't tell you what the limitations are, but we have readily used 10-watt mimics. In fact, we've developed mimics operating much higher than 10 watts with substrate thicknesses of 100 microns. And that doesn't appear to be a problem. But again, off the top of my head, I can't tell you what that limit is. It's undoubtedly higher than the CPW structure, which is going to have a much finer geometry. In other words, middle to the center line to the ground planes is much closer than 100 microns typically. And so power limitation, the CPW is going to be much less than microstrip.
Right. So the next question is, does the speaker see potential in the new gallium oxide technology?
Yeah, you know, people have for years have been trying to use various oxides of, first of all, for gallium arsenide. There was, I remember maybe it's 30 years ago now when some French researchers reported some amazing results using gallium oxides in an MOS type structure with gallium arsenide. Some fantastic power densities, and people were amazed at these results. Well, it turned out these oxides have reliability issues. They don't last very long. They're not stable oxides. They degrade relatively quickly. And what I mean by quickly is in hours and certainly days, they degrade and they're not useful. Silicon oxide, silicon is blessed with an oxide that is very stable and can be used, you know, as well as silicon nitride is another good passivation material for silicon devices. But unfortunately, with gallium arsenide and also GaN, there are no native oxides that can be used, at least reliably.
Right. The next question is regarding the foundries. So are the US-based foundries are open to give access to international universities?
Yeah, I believe so. There are some restrictions in some cases. An example might be HRL laboratories in Malibu. I know that they are available. Some of the well, I have to qualify that. There are some processes that were developed specifically under government contracts and are restricted to US-based companies. Now, in other cases, there are other processes that are open. Corvo, I'm aware of. Corvo's processes, to my knowledge, are wide open. Anyone worldwide can use those processes. Win Semiconductor is another foundry in Taiwan that is wide open to anyone worldwide.
Right. So the next question is regarding the performance of the Cree GaN foundry. So the question is, how is the performance of the Cree GaN foundry?
Yeah, I didn't list Cree in my list of 6, as you might notice.
Mm-hmm.
And the reason I did is the performance of their mimics at 30 gigahertz. They have a process, a 0.15 micron process, as you may be well aware of. But the performance of that process is just not up to the level of the others listed. And in fairness to Cree, they are making improvements to that process. So I haven't checked their process recently, that is the last 6 months. So if they have made significant progress on that process, I'm just not aware of it at this point. But when I provided or did my research on the foundries, Cree just was not up to the level of the others in terms of performance.
Right. There is another question. As you know, in the talk you have mentioned about the cost of the GaN fabrication. So the question is, will the cost of the GaN fabrication come down ever to the level of CMOS?
Yeah, that's a good question. If you're asking if it'll come down to the level of CMOS, I don't think so. I think it's always going to be higher than CMOS. The question, I think, is the level of performance provided by GaN sufficient to justify its incremental cost? And hopefully, with time, that increment in cost will come down substantially. And I believe it will, certainly with high volume applications out there. 5G hopefully is that application, which is a driving force behind the industry to improve the processes and to drive the yields up and the prices down. So the basic answer is no, it'll never reach CMOS, in my opinion. There'll always be an increment there, but is that increment in cost worth the extra performance? That's the question.
All right, so increments shall be in terms of performance that is provided by the GaN. So right. Thank you very much, Dr. Jim. That's it for the questions, and it's a really interesting talk regarding the GaN power amplifiers and its trends. So I hope in the future we'll also host you again on some other related topics as well. And thank you very much again for your time and the talk.
Well, thank you all. Bye.
Thank you very much. Have a nice day. Till then, bye bye.